I want to talk this morning about um, assumptions and problem solving and statistics. I apologize a bit. I'm in my best painting T-shirt this morning, so I'm about to go out and paint the side of my house. But I got thinking about this and thought I really would like to add this in this morning for your consideration as we're working through the semester. In an earlier chapter, I provide some materials about steps in problem solving. Uh, and I didn't talk about it much then, I don't think. I may change that future semesters. But one of the things I'd like to do is sort of take that another step with you here. This week, the week on discrete probability distributions, I talk about a problem if you have $10,000 to invest and there's two different options and gives you some things about it and so forth. And I work the problem out and give you a way to work the problem out. I was just reviewing that this weekend, and one of the things that occurred to me is like, and my answer is exactly correct given a specific set of assumptions. And you can assume different things and you might get a different answer out of this one, slightly different. You'd come to the same conclusion, I think, that I do, but you could come up with different answers. And one of the things that I really want to just highlight is when people think of statistics as a mathematical science, what we tend to think of is, well, mathematics, you use a formula and you get the answer. There's a correct answer, and there's a tendency to want to get there with it. And that's true. And in a lot of statistics, there is a answer. Once you get to a certain formula, a specific formula, you start putting numbers in, there should only be one answer that comes out of that process. However, the question is, well, which formula? I was just reading an article in the New York Times about whether the article was, what are the odds that these two Justice Department senior people who got randomly audited by the IRS really was random? And they went through all the stuff, but how would you figure that stuff out statistically? And that's pretty interesting. But one of the things that the big takeaway for me of the article is, well, it depends on what set of assumptions you use and how you define the problem. The answer to that really, the mathematical part of it is in some ways fairly straightforward. The deciding on the assumptions that you're going to make in the process and picking out the formula that you're going to do with that, how you're going to define things, that makes all the difference in the world. And you can come up with something that's like somewhat unlikely to really, really unlikely, depending on the set of assumptions that you make in the process. One of the things that I've been trying to push a bit in here is, I talked about this the first week, that being aware of the type of numbers you're working with. Are you working with nominal data or ordinal data? Are you working with discrete data or continuous data? These are all sort of underlying assumptions about things that you have to be clear about in order to figure out which formula and how you want to go about working with things. This week, the problem I provided in one of the other videos is about trying to figure out the average of a discrete probability distribution, or the issue comes up is expected value. And the problem I present is, so you have $10,000 to invest, and you invest in these things, and there are three possible outcomes. And one of them, you lose the entire $10,000. And the second one, at the end of 6 months or something, you have $20,000. And the third option is the end of 6 months, you have $100,000. Now the question comes up in that, and I start with the assumption in that process that if you, at 6 months, you have $20,000, what you have gained is $10,000. You had $10,000 before that. But that $10,000 from me is, in economics they call it, it's a sunk cost. You put it in and it's sort of gone. Now, if you lose everything, it's like you've lost your $10,000. If you get $20,000 back, did you gain 10,000 or did you gain 20,000? And that's not something, it's like, there's not a right answer to that, I don't think. There are different answers to it, and your mathematics would change to some extent on what assumptions you make about that process. A lot of this, I'm trying to present statistics to you as tools to help you solve problems and make decisions. The key point in the thing I want to say to you is how you define a problem defines how you will solve the problem. If you define a problem differently, you would solve it differently. And I'm gonna move out of statistics here and talk about this in a different kind of context. I had a person ask me recently to try and say, I'm trying to figure out whether I should go back to work in healthcare. I went, well, that's a really good question. I think that's really, it's worth thinking about. He said, however, it's a slightly different question about, should you go back to work? Should you go back to work in a hospital like you did before, which is as a nursing assistant, which what you were doing before? That's one question. A different question altogether is, how should you think about supporting yourself? And how should I look at supporting myself financially versus should I go back to work in a hospital and healthcare like I did before, are really different questions, and they will lead to different answers. The same thing's true as statistics. How you define the problem becomes really important. And there's a tendency for a lot of us, particularly introductory statistical stuff, to say, they want to think about this as like it's all algebra. Just find the right formula, stick the right numbers in, and you get the right answer. And there's truth in that. But when you're problem solving, defining the problem correctly or accurately is half the problem. And doing it badly means that you'll get the wrong answer. Or you'll get an answer to something, but it may not be the question you want the answer to. I've suggested this in another context about surveys. For me, it's like I've done a number of different surveys in my life of different kinds, and I feel like one of the things I do first when I've done surveys, when I got better at it, or smarter at it, is I would take my survey and I would administer it to 10 people who I knew. That's called a convenient sample. Now, and what they would people would say is, you don't trust that kind of data. And I would say, absolutely you don't. Well, that's not that you don't trust it. It's you don't bet the farm on it. You realize it gives you some information, give it to 10 people you know, but it doesn't necessarily tell you what you want to know. And the second thing is, if you give it to 10 people and you hear how they answer the questions, you sometimes realize, and I often did this, is kind of what people are not answering the questions that I thought I was asking. I'm asking something, but they're answering something that's totally different than what I thought I was asking. And realize I got to go back and redo this my questions, because what I'm learning is what I thought I was asking was not what people were hearing. The same thing's true in an awful lot of research, is that people go and do research and they get to the end of it and it's like, when I get here, and part of the problem is the question they started with wasn't a bad question, but when they get the answers back, they realize that doesn't answer what they really wanted to know. And then they are, if you're honest, what happens at that point, you end up saying, oh, I didn't formulate my question well. So I got an answer to a question, but not the question I wanted to ask. One of the things I encourage you to do when going through particularly word problems, as this one becomes bigger the more we get further into this course, is that if you have any question at all, any confusion about it, take the time to write down what exactly is he asking me for here? And what exactly do I know in this thing? Because putting those things together often will point you towards a specific formula. For instance, If you're looking at your data and say, well, I know a proportion here of people did such and such, and yeah, one of the things you know, if you have a proportion, probably, or maybe, if it's a proportion between two things, you can probably have dichotomous data, which is nominal data. So you need to think about, oh, in which formula works for nominal data? It's important to think through sort of the underlying things you're thinking about. The research, I have seen articles that say, people say, wow, this is a really good article. This is really good, interesting research. And people read it over, and eventually somebody says, yeah, but you're assuming this data is normally distributed. And I don't think that's true for this reasons. And normal distribution of data becomes an assumption as we get further into statistics more and more. And if that's not true, then the formulas may not give you valid answers. With correlation, I try to push on that. So I'm saying, we typically assume, I mean, it's like we get a correlation. You know, it's like it's either you get a number. But if you're starting with dichotomous data for one of the variables, then you probably shouldn't be using the Pearson product moment correlation for that. You should be using one of the other ones. What's going to come up here in this chapter particularly is you're looking at distributions. Well, what kind of distribution do you have? What kind of data is it? Particularly with discrete probability distributions, you're dealing a lot with proportional or dichotomous nominal data is a common piece in this process. And you just got to think through, there are assumptions behind all these things. And being aware of those assumptions helps you figure out, well, where's the best match? Which match works for this kind of data and the things I've got. So there's a point before, it's funny to have a math teacher saying this to you, but it's like, be cautious about jumping to formulas too quickly until you know what exactly is being asked about. And to some extent, I would say if you get really confused and can't figure out how to answer something, what you should submit to answer for me is your best assumption, your best statement. What's the problem being asked for here? Because that's an important piece that you need to learn how to do. It becomes an important piece of the overall process. This is about problem solving and decision making. And it's not wise to assume that I have defined my problem or I've defined my decision well at the beginning and just jump into the numbers. There's a part of me says, to be a good problem solver using data, you take a step back and really think about, what am I asking? What do I want to know? What am I really measuring here? What do I need to know at the end of this process? And then go to the data collection and start to figure out how to work with the data. Just some odd thoughts I've had this morning that I think it's important to think about the stuff that you're working on this area. Good luck this week.